guys, so let's see. Let's go here to the camera. There we go. So the last thing we did, okay, so last time we derived the TDS relations, the German expressions, and then for an ideal gas or ideal substance. Okay, let's try to take this from here. Okay. So ES 305 412-18. This is lecture 20, and this will be page 116. Okay, so what did we do last time? We derived the TDS relation. So very quick, I'm going to do a little summary of how we did all this stuff. So first thing we had, we rewrote the first principle of thermodynamics under this form. And then we had the equation, which was the new equation that the change in entropy, or the entropy S, the definition was equal to delta Q over T. Okay? So from this equation, we know that delta Q is equal to TDS. So we replace this delta Q equal TDS into the first equation, and we got TDS plus the work equal du. And then all this is a review, okay? What is the work done by the pressure? Minus PdV, so we had TDS equals to PdV plus du. And that was, that was our first TDS relation. And then we rewrite it in function of H, the entropy, U plus PV. So we ended up having the other TDS relation, that TDS was equal to dH minus VdP, I think it is, yeah, minus VdP. Okay? Then we did a quick review. What do we say for a substance that does not change its states? We know du generally is equal to U2 minus U1, but if the substance does not change state, this is equivalent to CVDT. And dH equal to H2 minus H1 equal to what? C sub PDT. And using the ideal gas relation, PV equal RT. So using these equations and substituting to these two equations, we ended up having the other two TDS relations that were change in entropy. One was equal to C sub V log T2 over T1 plus R log V2 over V1, and then using this one, so substituting to the first one, we got this one. Substituting to the second one, we got C sub P log T2 over T1 minus R log this is what we did last time. Okay? Okay, so there are different cases. Generally, I don't like to do this kind of stuff because it becomes like cooking recipes, but just for the understanding. So what is an incompressible substance? Any idea? Water, okay. Gases are compressible, no?
Oh, yeah.
But what is a good example for incompressible? So basically, what it means is that okay. So basically, if it's incompressible, you cannot change its volume, no? Okay? So we could say what? In this case, for incompressible, let's say we can say V1 equals V2. So this will mean what? Log V2 over V1 will be equal to what? Log of 1, 0. Yeah? Okay? So basically for incompressible substance, really the change in entropy is equal to CV log T2 over T1. But again, this you can derive it very easy because if you know it's incompressible, what will you do on the derivation is that you will put the dV is equal to 0. So I don't want you to memorize this, it's just for the understanding. Now this is the part that I need to look at because I don't like it, to tell the truth. Doesn't add anything to the problem, so this will help for this one. Now let's look at this equation over here, the second one. All right. And again, it's related to the table, so. Okay, so recalling. The equation delta S equal to Cp log T2 over T1 minus R log P2 over P1. Okay? So I have some equations here. These I never showed this one, so I need to look at it. Okay, so all this stuff is using ideal gas tables, which I don't like to use, okay? I have to tell the truth. Every time I can do the calculations, I do the calculations. I don't like to use those tables. So because of this, you're going to see right now, basically using ideal gas tables, they define S sub A, S upper sub integral of Cp dt over t. Okay? So that equation star becomes delta S equal to S sub O T2 minus S upper T1 minus R log P2 over P1. Okay, so let's see. In other words, let's see if I can go here. All this, I'm going to be honest with you, I don't like to do it. You probably have to do it in some programs, but okay, this is this. Why don't we come here? If you come here, ideal gas properties, ideal gas, so table 822, 823, 963. Let's see if that's true. So ideal gas, you see on these relations, this is for air. You have this S upper sub O over here, no? Okay? So what is the meaning of that S upper sub O? Is the same thing as basically this term over here. That when you assume Cp to be constant, what happens? This becomes Cp. You can put the Cp outside the integral sign, and the integral of dt over t becomes the log, no? But if you assume the Cp is not constant in function of the temperature, all right? So then if Cp is in function of the temperature, can you take this one outside the integral sign? No. So what happens then is better to use this for the air, okay, or some gases. So it's a better approximation, but it doesn't change anything. But I hate it because you need to go to the table, find these values, then you need to find the R for the air, and you need to subtract this value over here, no? Okay, so personally, I don't like it, to be honest with you. So let's see these other relations that sometimes we need. I have them here, okay? I'll be honest with you. This is maybe the first time I went to the textbook and printed 2 pages, okay? The relations we derived, these ones over here, very small, but basically these are the ones we derive. So they give you relations between Cp and Cv, which I think you know, but we can write them down. And you see this is the one I use here. So just in case we use them, Cp equal to Cv plus R. I think I gave you those relations already. And let's see, I think there's another one. And then what else can we say? Yeah, and gamma, what is gamma? Gamma, I think, is Cp over Cv. Yeah, I think that's what it is. And then we have the other 2 relations. Cp equals to gamma R divided by gamma minus 1. And C sub V is equal to R divided by gamma minus 1. So let's see if that's true. So Cp equal, yeah, it's correct. So I think I told you these relations, you can put them, remember that page with all the units? You are more than welcome to write them down, okay? I have 0 problem with that. I'm not testing your memory. Okay, it's like me. I mean, I kind of know them, but double check because it's still the way it is. Yes.
Is that R bar or is that R for the specific gas?
This is, let me check because I have them here. This is, I know I have them somewhere, but okay, I didn't take the page. I think it's the R.
Okay.
And the R is actually the one specific for the gas.
For the gas, yes.
So the R is R bar over the molar mass, no? Okay, so for once, instead of going, because we are approaching the end of the semester and I assigned the homework, so instead of just going and select problems randomly, before coming to class, I look at the numbers that you have on the homework, and I try to pick problems that were close so that to see if they are similar, no? Okay? Instead of doing something completely different. But I'm actually going to start by the end of the homework because this is the classic problems about this. So I pick 661. Oops, that was page 117. Okay. Page 118, we're going to do problem 661. Okay, so, I mean, I have here the solution, but it's not important. It's just, let's do it like if we knew nothing about it, which is the way it should be done. So 661. So we know this, we don't know this, we know this stuff. Oh no, we don't know any of that stuff. There is more than what we're going to cover over here. 61. Can you read 661 over there, or is it too small? Maybe I can do it a little bit bigger. Alright, so let's go. Let's see if everything's going to fit over here, more or less. Alright, so 661, we just needed to read the problem. So let's see. A 2.64 copper part, initially at 400 degrees Kelvin, is plunged into a tank containing 4 kilograms of liquid water. So let's see. So let's say this is our tank. This is our water. And what are we doing? We are plunging a copper part, so I don't know how to do this. So we know the mass of this stuff is M equal 2.64 kilogram. I don't know if it's important if it's copper or not. I don't think so, but maybe it's important, I don't know. So what do we know? Maybe for a specific heat, yeah, we might need that. So initially, okay, so the copper initially, so let me do an orange, is at 400 degrees Celsius. It plunged into a tank containing 4 kilograms of liquid water. So MW equal to 4 kilograms. Okay, initially, so T water So let me call maybe, I don't know, TWTC. The copper part and water can be modeled as incompressible. Okay, so what does that mean? dV equal to 0, no? Okay, so is that important, incompressible? It might be important, so incompressible. Basically means what? The initial will be equal to the final, so basically the change in specific volume or density is 0. Okay, that's what it means. The copper is incompressible with specific heat, so C okay, so specific heat of copper, C sub C, 0.385 kilojoules per kilogram Kelvin, and the specific heat of the water, 4.2 kilojoules per kilogram Kelvin. For the copper part and water as a system, so what is our system? Okay, so you see, guys, that I spent a lot of time setting up the problem, no? Oops, maybe I need to kind of move this one a bit to the left. Okay, so I don't know what to do with this. Well, I'm gonna have to go down to this 110. Okay, I think that's gonna work. So for the copper and the water as a system, determine the final equilibrium temperature in Kelvin and the amount of entropy produced within the tank in kilojoules per Kelvin. Ignore heat transfer between the system and its surrounding. Okay, so ignore heat transfer. What would that mean? Q equals 0, no? There is no change on the temperature. So part A, we need to find basically what is the temperature of the mixture, no? When you mix the water and the copper. So there's two different ways to do this, but this is generally the way I do it. Is okay, so part A is to find, let me do everything. So part A is to find T final. Part B is to find delta S, what is known as the entropy production. So in the book they call it sigma, but we don't use that. Okay, so now we can eliminate this stuff for you. Okay, so over here for part A, what we could use is what? First principle of thermodynamics. What is the equation? Heat plus work equal to change in energy, no? So in this point, do they tell us to ignore the... Okay, so they don't tell us to ignore, but I think I don't see another way to do it, okay? So over here, we're going to ignore energy. So what does that mean? Okay, du delta u. Okay, maybe I should do even more stuff, but we get to this equation. Now, do we have any heat being added to the system or removed from the system? They tell us to assume it's zero, no? Is it any work? No. Okay, everything comes from the figure. I'm not making it up, okay? You make a figure, you do it from the figure. So we ended up having what? There is no, if you want to look at it that way, but there is no arrow of pressure or anything, no? There's no pressure change and nobody's adding work. So there's no work. So now you get to this equation and then you're like, okay, and now what? No? Alright? And that's generally what happens. But if you think a little bit about it, what does that mean? I mean, first we know that delta U can be approximated by what? If you don't change the state. CV, yeah, CV delta T, no? Okay? So we can say that this one here is equal to the one of the copper plus the change in internal energy of the water is equal to 0. So this will mean what? So you are right, we need the M, because they ask us to find, they give us the masses over here. So this will mean what? Mass of copper times C of copper. Yeah? What is the delta T over here? Will be what? Will be the final minus the initial, no? Yeah? So with the final is what we are looking for, no? And what is the initial temperature of the copper? Yeah, but I think I call it T sub C, no? Is that correct? Yeah. T sub C plus now what? The total change in internal energy of the water, which is M water, C water, T final minus T water. All this should be equal to 0. Okay, this is a classic problem for this chapter, okay? The most classic problem. So over here, what is the only unknown? Do we know the masses? Yes. Do we know the specific heats? Yes. Do we know the initial temperature of the copper and the water? So the only unknown is the final temperature. So we can solve for TF. Is that I zoom in and I think run out of space. So now what could happen? So let's see, if I do the algebra, you will have T final, you can factor by M sub C, C sub C plus M sub water, C sub water. I'm moving it to the right hand side, and then I'm moving the other terms to the right hand side, will be equal to M sub C, C sub C Tc plus M water, C water, T water. So at the end we have that the temperature of the water plus the copper piece would be equal to M sub C, C sub C, T sub C plus M water, C water, T water divided by application. What do we get? What is the mass of the wall of the copper is 2.64. So I think units are going to work out. I don't see any strange units. C of the copper is 0.385. Temperature of the copper is 400. Plus mass of the water is 4. C of the water is 4.2. And temperature of the water is 300 divided by 2.64 times 0.385 plus 4 times 4.2. So for once I have the values, but I want you to give me the result, okay? It's a way to check. So just use the page to check, okay? Somebody else is not far. Here they have 300 and I don't know if it's 305.6 or 306.6. I have no idea.
305.7.
305.7. Let's go with your results, okay? 2% goes 305.7. I mean, it's not that important, okay? Okay. So now, part B is to find the change in entropy. So do you remember the concept of entropy was introduced in order to do what? To give us an answer about what? Okay, but to know if a process was reversible or irreversible, no? So what do you think? Do you think this one is irreversible? Do you think that if you pull now the copper from the water, is it still going to be at 400? No? And when you pull it out, the water, the temperature is not going to be 300, no? It's probably going to be more. So if we think about it, just to think about the result, here we should have what? Should we have the change in entropy equal to 0 or be different than 0? Different than 0. This is not reversible, it's irreversible, no? Okay? Okay, so let's see. So part B. So I think we say if we use the concept of increasing entropy of the universe introduced by Kelvin, we say that the total change in entropy is equal to the change in entropy of the with the surrounding plus the change in entropy of the system, no? And if you remember, I said that this one in 90% of the cases is equal to what? Delta Q over T plus delta S of the system. They call this sigma, I think, on the textbook, but yes?
What's the word on the next delta? The first delta S? Delta S is equal to delta S.
Surrounding.
Surrounding.
Yeah.
Thank you.
So basically, what would that be, that term? Is it any change of heat with the surrounding? No. So the Q is 0, no? Yeah? I mean, I'm not making it up. Everything comes from the figure, no? Okay, that's why I say figures. So this one will be 0. say cooking. They go and give you right away one equation. I don't want to see that. All right? So what type of problem are we dealing here with? Closed system or open system? It's a closed system, no? All right? So for closed system, we know, so for closed system, I go a little bit faster. What do you know? The first law of thermodynamics will be equal to what? Delta Q plus delta W. We neglect kinetic and potential energy, so this is equal to du. What is the definition of the entropy? Delta Q over T. Okay, so I do once more, but delta Q equal to TdS. Okay, I'm going to start going a bit fast, okay? So we know the change in work will be equal to what? Minus negative PDV. And du, do we have a change of state between the substances? Is the water changing state? Is the copper changing state? So we could say approximate this as what? C sub V dt, no? Okay? So if I combine all this stuff, I mean, I'm not going to combine it at once, but let's say this will become what? We can rewrite this as TdS minus PDV equal C sub V dt, which is the same thing that we did when we did the derivation. Okay? But what is the difference between, I mean, here you show me that you understand what you're doing. So from here, I mean, we could simplify now if you want. Let's simplify now. That way you see you can go a lot faster. Since the system is incompressible, what does that mean for dV? Okay, we put it over here, no? Incompressible, dV equal to 0, so really there is no work, there is nothing doing work, so it means incompressible, so this is equal to 0. So that means what at the end? That we're going to have, let me continue in blue, TdS equal to CV dt. Okay? I mean, ODS equals CV dt over t. Start going a little bit faster, okay? So what are we trying to find over here? We're trying to find the change in entropy, no? Alright? So now, what can we do in order to do this? Yeah, so let's say between initial and final. So this would be initial and final. So basically this is going to give us what? The change in entropy will be equal to what? Here's where we need to be a little bit careful. So will be log CV log T final over T initial. But again, how many substances do we have? 2. So we need to do this. So maybe I should know this. Let's say for the copper, no? What is the change of entropy of the copper? Plus something similar for the water. should be the T initial. Here is T final, the one we calculated. This one should be T copper, no? And this one should be TW, and this one will be what? C sub C, and this one will be C, the specific heat of the water. So if we do the calculation, this is a classical problem, and it's good for the understanding. This is a very good problem. So the C of the copper was equal to 0. Oh, I forgot to multiply by the mass, but who cares? Okay. It's not going to change anything. 0.385 log. What was T final? 305.7 divided by 400. Okay. Plus, I think it was 4.12, 4.2. Log of 305.7 divided by 300. Okay, so over here I want you to do the calculations for me and give me one time the value, one of the values at a time. Okay, negative what? 0.104. Okay, the solution has different values because they multiply by m, but who cares? Okay, guys, I know I say it doesn't matter, but actually it does matter because the mass is different for both of them, no? It's not going to change anything to what I want to say, but I don't want to give you something that is not 100% correct. So would you mind here maybe multiplying this one, sorry for that, by add over here m sub c, add over here m sub water, so that will be what over here? 2.64. It's not going to change anything, but I don't want to do something that then you're going to say is wrong, okay? So then this one will become what? 0.4, oh, I have no idea. You see, it doesn't change anything because the values have really no meaning over here, but it's just the sign. But the important part over here is that you're going to get a negative value over here. So what will be your negative value? .273. And now the next one should be a positive value. 0.316. Okay, so let's stop over here because really the magnitude of the numbers we couldn't care less, okay? To be honest with you, it's not that important. But basically the first term is for what? Is for the copper. So if you think about the energy, what's going to happen to the copper? Is it going to gain or lose energy? Losing energy. So the negative sign over here means that it's losing energy, no? What's going to happen to the water? Is it going to gain or lose energy? It's going to gain energy. That's why we have a positive value. Now, 0. So what are we going to get over here? We're going to get something equal to 0 or higher than 0? Higher than 0. And why Kelvin introduced the concept of increasing entropy of the universe? Because we said that in not a perfect world like this one, every time we do something, in most cases what's going to happen, we're going to waste energy and give it to the universe, no? Yeah? So the entropy of the universe is just going to keep increasing and increasing, correct? Unless we only have reversible cycles. So we do this, so basically that means the negative sign means lost energy. The positive sign over here means gain energy. So at the end, what do you have? Delta S equal to how much will be 0.120? Yeah. 0.0. Okay. So we know this is 0.043. Yeah, that's what. So this is positive. So what does that mean? It is irreversible. Okay, any question about this problem? Did you understand it? Okay? But again, remember, this is like I say all the time, it's like watching sport on TV, no? I'm the one doing it. Alright. So this is a classic problem. I'm not going to say you have that on the example. Let's say you have a lot of chances, because this is really one of the classic problems about this chapter. Maybe not this one, but you can expect to have something similar to this one, okay? Unless something very strange happens. But so 17, 16, okay. So let's go to page 121. Okay, and I pick another problem here. I don't know which one to do. Okay. So I guess this one that's the last one. Let's go now to the first one I have. Let's see which one looks a bit more difficult. I want to make sure I can finish. Let me do the easy one. The other one is 2 pages. So the problem I pick over here is 637, which I think you have 635 on the homework. So 637. I say you have 637. So let's see what 637 is. Okay, it's funny, I started, you see, by the end. Oh, wrong direction. So 637. Alright, so let's see. 2 cubic meters of air in a rigid insulated container fitted with a paddle wheel. Okay? Okay, I will do something like this. It's not too pretty. So it's insulated. So what does that mean, insulated? Q0, perfect. So you see, it's important to read the problem statement, no? So insulated container fitted with a paddle wheel assuming the ideal gas model. So ideal gas, what does that mean? PV equal RT with CV of the air, which we know 0.72 kilojoules kilogram Kelvin. Determine the mass of air and the final temperature. So the final in Kelvin, and C the entropy production. Okay, so how can we find the mass? What is the relation we can use? And we need to find a relation that relates to the air, no? Am I missing? Oh, I forgot something here very important, which makes the problem very easy. The volume. So 2 cubic meters. You see, I was thinking about how can I do this? And it's because I forgot to put something.
Is that kind of weird?
Huh? I know, I said that's probably why I missed it, but guys, you see, this is the difficult part to me, okay? I think now I kind of have everything figured out. That was the only part that I was like, how do you do the mass? But now that I see the volume, what is the ratio we can use? If we use the ideal gas relation, we use PV equal to RT, no? Do we know we can say P1 equal to V1 RT1, no? Yep. So do we know T1 and P1? T1 is 293, P1 is 200. What would be V1? V divided by M. And what would be R? R bar divided by the molar mass of air, no? Yeah.
What happened to the number of moles in the ideal gas law?
No, because if you do this, let me write it down over here for you. If you use the ideal, this is different. The ideal mass model is PV equal nRT. We wrote here PV equal RT. I think it's this one. So N is what? Is mass over molar mass. So I think the R something happens, okay? Yeah, this V is not the same relation, okay?
Yeah.
They are equivalent, but it's not the same one. So basically, if I start substituting, this equation becomes what? P1, because I don't want to do the you can do the calculations, but I'd rather find the expression here, V over M solve for m, what do I get? V1 times V times the molar mass divided by R bar and all this divided by T1, no? Okay, so M I think was from table A1, no? M is down. For me it's always 30, but here is 28.97. Okay, from table A1, 28.97. And what is R bar? I think it's the 8.314, something like that. Okay, so I think the unit should be okay. But I mean, you see, I don't do the stuff for the units anymore. You have to do it for check, okay? So M will be equal to what? So 200. Yeah, but I think they're gonna cancel with this. These are kilojoules, no? So I think those three cancel out. So 200 times 2 times 28.97. I think the unit should be okay. Divided by 293 times 8.314. So for once, you see, I can check. So what do you get? Here they have 4.76, whatever you want, 4 points. Okay, so part B, which is to find the final temperature, we probably need to do this, we need to follow exactly the same procedure as we did before, no? Okay? So part B. So 122. Part B. So I start going a bit faster. We have Q plus work equal change in internal energy since the Earth does not change state, we can say delta U is equal to what? mCV delta T. Yeah, start going a bit faster. Now, is it any heat in the system? You see, everything comes from the figure. Is it any heat? Is it work? Yes, so we need to keep it, okay? So from here, from that equation, we can get that work really would be equal to what? mCV T initial, so T final, minus T initial, which is T1, no? The 293. So from here, we can solve for T final, will be equal to what? Work divided by mc sub V do the numerical application. First, let's have some type of guessing. Should T be higher or lower than the 293? Higher, no? Okay. So over here, what is the work? The work is the work coming out or going in? Going in. So that means is positive. So, and the value is 710. So we have 710 divided by the 4.76 that we just calculated, times C is 0.72 plus T1, which is what? 293. What do you get?
500.17. Yeah.
Okay, let me see what they have here. Wow, yeah, 500? Okay, 500.17. Okay. Okay, so now this problem over here, how do we do the change in entropy before? So ignoring kinetic and potential energy, we have this is equal to du ds equal delta q over t Okay, so I'm going to start going a bit faster. We know that delta W is equal to minus PdV. So what do I get if I substitute all those terms? We get TdS minus PdV equal to what? Maybe I forgot to put it here. What will be du? mCV dt. Same as before. So in this case, now, what is this? This is a rigid tank, no? So is it any change in volume? No. Okay? So in this case, air is compressible. It's not because it's incompressible, it's just because it's a rigid tank, no? In this case, what would be then dV? 0. There is no change in volume, so there is no work. Constant volume, no work. So we have again the relation TdS equal to mCV dt. ds equal to mCV dt over t. So here we are assuming the mass and the CV to be constant. So at the end we have that the change in entropy will be equal to what? mCV log bit faster because I just want to finish. So delta S will be equal to what? Okay, 4.76 times 0.72 times log T final, which is 500.17 divided by 293. What do you get?
1.83.
Okay. So again, this is a positive value, which we expect. Yeah? So it's different than 0. So what does that mean? This is irreversible. Okay, guys, one thing. I was just thinking this morning, I think I told you I will do it because I always say it, but sometimes maybe I don't do it with a percentage, but I always say I don't care about the knowledge working into the class, but I have to judge the knowledge you're going to work out of this class, no? Okay? So I know grades are not being that good so far, so we have exam 1, exam 2, exam 3, and you have the homework, no? So I think, that's what I try to do all the time because I don't know what to do, but I think right now we have this. Okay? So I'm going to keep this. When I give you your final grade, I'm going to keep this one over here, but I'm also going to do this. And I will take whatever is the best for you. Does that sound okay? Because then if I do this, I really give more weight to, I will judge the knowledge you will leave the class with, no? Is that okay with you guys? So it's not that I'm going to do either one, I will do both, and whatever gives you the highest final grade, I will pick that one. Yes?
Is our final cumulative or no?
I mean, it's what we're doing now. It's it builds it. So, but basically, it will be on those chapters we have done, which are what, like 5 and 6. It will be chapters 5 and 6 of the textbook.
So you want to take the better of those two?
I take the best of the two options. Yeah.
For the individual?
No, for the individual. I mean, you know, because I always say that, but if I do 30%, then I don't give more importance to the end. Okay? So I will do both. I mean, if you put the work, I don't mind to help you, but you need to put the work, you know?